Hello everyone, welcome to our online course for data analysis and statistical inference for psychology undergraduates. And this is our second topic, descriptive statistics, within the first module of basic concepts, descriptives and central limit theorem and normal distribution, basically the descriptive part before the inferential statistics. So let's see what this lecture is about. First of all, let's talk about frequencies, because this is a very important basic idea. So when we're dealing with frequency distributions, we have to make a big distinction between qualitative and quantitative scaled variables. We talked about this on the last lecture. And frequency distributions are summarized in chapters 2 and 3 in the minimum book. So for qualitative variables, nominal, ordinal, or grouped scores of scale type variables, we can calculate absolute frequency, that is raw frequency. We will turn to this in a moment, how to do this. We can have relative frequency values, that is proportion and percentage, and cumulative frequency, which is probably a new term for most of you. For quantitative scales, on the other hand, I will show this in the second part, we have to make grouped scores, class intervals, in order to be able to draw a histogram or a polygon. I will show you guidelines for forming these class intervals, and we will construct this group data frequency distribution in a moment. But first, let's just simply take data from midterm grades. This is the raw data. First thing to do with it is sort it, and these are qualitative variables. Here we have grade 1, 2, 3, 4, 5. Grade 1 could also mean fail, and grade 5 means perfect. That means we can order it. It's a nice, let's say, ordinal type variable. So once we have the sorted data, we can calculate simply by counting. Okay, I have 1, 2, 3, 4, 5 ones, absolute frequency, which is 24% of the 21 total grades. Similarly, you can do this for all the rest of the grades and draw a nice histogram of the frequency distributions, where frequency is on the y-axis and grades, values of your variables, are on the x-axis. Now, this is relative frequency, relatively easy. Let's turn to cumulative frequency. What does that mean? These are the numbers that you will have for cumulative frequencies, and the last value of the ordered values will always be 100%. But why 38? Why 62? Let's dive into this. The first value, grade 1, is the same as the relative frequency for cumulative frequency, because we added up only this single value. But for the second value, grade 2, we have to add up everything that's beneath that. So 24% plus the 14% adds up to 38%. We do the same for grade number 3, arriving at, from these three numbers, 62%. Then for grade 4, all of these will be 76%. And last but not least, grade 5, where we have the 100% for all of these numbers. Let's turn now to quantitative scales. Here we have to do something called a grouped data frequency distribution, and I would like you to be able to do this by hand, although SPSS or JASP will do it for you. So this is the recipe. find the highest, lowest score, define the range, decide on the interval width, can be anything, but make it reasonable, determine class intervals, use the tally system, simply counting how many actual values fit in within these intervals, and then sum the number of occurrences. Please try to do this, okay, based on this little description. And let me show you in a moment how this looks like on a real database. Frequency of reaction time data is listed here. I have the raw data, which I sorted, okay. I determined the class intervals a priori. And now simply I'm going to count how many actual values, raw values sorted, will fit into the first interval from 100 to 109. And I can see that there are 5 of these values. How about the next one? Only one value, 112, fits within 110 and 119, etc., etc., etc. Okay, so you do this for each interval, and this is a typical distribution for a reaction time study, which can be graphed, showed on this nice histogram, where we see that most of the people try to be fast because that was the idea, that was the task, and we have a few different values on the longer reaction time ranges. Histogram or polygon. Basically, it doesn't really make a difference once you want to show your frequency data. For histogram, you simply show the percentage according to the values. If it's a continuous scale, then you simply pick the middle value of each interval and present that on a histogram. Whereas on the polygon, by simply connecting the top middle points, you have a nice continuous feeling of the data. But these two data sets based on the distribution of birth weight for newborns, quite a lot of them in Hungary, are exactly the same. It's just a matter of taste how you want to present that. This was the first part, basically describing frequency distribution. And here are a list of useful formulas that you can find in the course book. And we will be using these formulas for these terms later on. Let's review now how to calculate central tendencies in descriptive statistics. So, measures of central tendency are outlined in Chapter 4 in the minimum book, and you should know how to calculate these measures by hand. We're talking about the mode, the median, the sample mean, the grand mean, and the population mean. Think about soccer. Obviously, in a little mini study comparing girls and boys, boys will have more hits in soccer than will girls. Then again, in verbal fluency, for example, girls will score higher on average than boys. This doesn't mean that there isn't a single boy or girl who is better than the other sex in, let's say, soccer or verbal fluency. We're just saying that generally these genders are different in this respect. So let's review these one by one. There's the mode. The mode is the score that occurs with the greatest frequency. We will always have a little box highlighting which criteria for which variable type you can actually calculate this kind of measure. And the mode is the good news. You can calculate it for qualitative and quantitative variables. If, and this is a big if, at least there's one value which is more frequent than all the others. Let's see a distribution, and here you can see that this is the value of variable x that is the most frequent. It's true that it's more frequent than the others. Whereas if you would have a flat distribution, then there would be no mode. Median. The median is the middle score if the observations are arranged in order of magnitude. And of course, sometimes you have an even number of data. Then you would have to take the average of the two middle scores. Otherwise, equal number of scores should fall below and above the median. This measure can be calculated only for ordinal and quantitative variables. Ordinal because they have to be ranked, right? So nominal values don't have a chance here. Let's again see an example for the median, and it is grade 2. Why? Because you have 10% of the students in grade 1, the first grade, and already 50% are in grade 2, so the middle score will be grade 2. How to calculate the sample mean, the grand mean, and the population mean? These measures you can calculate only for quantitative variables, since you need to be dividing things, so you cannot have this kind of measure for ordinal or nominal variables. The sample mean, or the average, is the arithmetic mean or balance point. About this balance point, there's a very nice video that you can check out on this link. Basically, you add up all the values and divide them by the number of elements. The grand mean is a little bit different. You need the grand mean when, for example, you're reading an article, you see a certain value for an interesting variable with a sample size, then you read another article. You also see an average, different average, with a sample size. Now, who to believe? Well, you can just sum them up in a grand mean measure, saying that you use this formula for the general idea which you have read in articles. Also, you can calculate the population mean even if there's no n value, only frequencies. For example, if you have a p-value and a certain value for your measure, you can just multiply them and add all these up, and then you will arrive at the population mean. Let me give you a good example for this. So let's try a few challenges in the next few moments, okay? Just testing your understanding of this topic. Let's start with the median. What is the median here? Remember, you have to go until you reach 50% of your data, and maybe, so it's grade 3 in this case, and it's maybe even easier to remember that the median is where the cumulative frequency reaches and leaves 50%. So here, grade 1 is no good for us. That didn't reach 50% just yet. Cumulative frequency is still just 38 here, but cumulative frequency is already and over 50% at grade 3, so that will be our median. Let's have another practice problem, typical at the exam. Let's calculate the population mean of midterm grades based on this distribution. As noted before, you have frequencies for each value of your variable. So you don't know how many people actually got this grade, but you know the proportion of people who got 1s, 2s, 3s, 4s, etc. This way you can simply calculate the population mean using this formula and arrive at a solution that is grade 3. Another practice problem where we're looking for the grand mean if we have different number of students scoring different number of IQ scores on average. It could be read from an article in my previous example. And here again, using this formula, you can calculate the grand mean and arrive at an IQ score of 107.4. Some useful hints I found very good when trying to memorize these differences in what can be used, which kind of central tendency can be used for which kind of statistical measure. For the mode, everything goes. Quantitative and qualitative variables are fine. However, for the median, just forget about the nominal scale, and you can stick with ordinal scales and up. Whereas with the mean, all you can have is quantitative variables. So maybe this is easier to remember this way. These are the useful formulas for central tendencies. And let's now turn to another very important measure, the dispersion measures or variability in descriptive statistics. Just looking back to the soccer game problem and cognitive verbal abilities of boys and girls, remember I told you some of the girls did better in soccer and some of the boys were better in verbal activities. So dispersion measures will actually tell you how true this in fact is for your specific data set. Let's look at the different measures we will talk about. I know there is a bunch of them, but basically starting from deviation score and ending with standard deviation and standard error of the mean, this is all the same story, only different chapters in the same book. Now, we have to note that all the measures of variability can be calculated only for quantitative variables. How far are the data points from the center? That's the main question of dispersion measures. So person number 1 is obviously a little shorter than the average, which is 173 centimeters. It's somewhere here. The dispersion measure, the standard deviation, plus minus 16.3 centimeters is kind of the average deviation from the center. And this is how we picture it. We take the mean and then we use something that we call the epsilon error bar, and we picture it the same value, for example 16.3 up and down from the average. Now the range is a very simple dispersion measure. It's the distance between the minimum and the maximum value. And let's see an example. What is the range based on these frequency distributions? So we have this frequency distribution on depression scores. The range is 4. Why? Because I have 1 and 5 as the minimum and maximum values, so simply the range is 4. Here Number of successful recalls from 1 to 5, same thing. 4 recalls is the range. Now, if we want to go into more detail, we have to have the other dispersion measures. So let's understand them. Let's start with the deviation score, which is the difference of a single score from the mean. So for example, in this previous example with height, we know that the mean height is 173 plus minus 16.3. We don't even have to know this number because for the deviation score, we need only the mean and the score of that specific person. For example, person number 1. And his deviation score is minus 10. He's 10 centimeters smaller than the average. 10 centimeters here. You have to have that as well. So person number 2 is obviously higher than the average. He is 26 centimeters higher than average. And I will put in the centimeters here on your notes. Okay, if we have the sum of squares, if we have deviation scores, we can sum them up. So we take the deviation scores, we square them and sum them up, thus arising at the sum of squares, which is another very important dispersion measure. We don't use it usually, which is use it to calculate the variance, which is the mean of the squared deviation scores. So here we take the deviation scores, okay? We sum that up, sum of squares, and we take this whole thing and divide it by what we call the degree of freedom, n minus 1, the number of elements in our sample minus 1. Why minus 1? Because it corrects for the larger versus smaller samples. If this number is really small, like 10 minus 1, 9, will count. The variation will be a little bit larger. Whereas for, let's say, 100 minus 1 doesn't count as much. So this minus 1 corrects for larger versus smaller samples. Please note that in chapter 5, they use n here, not n minus 1. It's like the taste of statisticians. Okay, once we have the standard deviation, we can, so the variance, once we have the variance, we can take the square root of variance and thus arrive at the standard deviation. Why do we do that? Because with variance, when we're talking about variance, the actual numbers, for example, milliseconds, with variance, we have milliseconds square as a result. Remember here, we squared it, we divided it by n minus 1, but it's still a millisecond square. So if we want to talk about milliseconds, we have to take the square root of variance and thus arrive at a single measure that we can, unit of measurement is more easy. And another important point is standard error of the mean, where we take the standard deviation, okay, and we divided it by the square root of the number of elements. We use this usually when we make inferences about the population. We will use it in many tests, statistical tests to come. It's kind of the most complex variability measure, and that's the end. This is just to show you, if you want to demonstrate your variability, for example, showing that picture naming response time is not only more slow for children, but it's also more variable. You can do it by adding the standard deviation on the epsilon error bars, but you can also use the standard error of the mean on the epsilon error bars. Basically, when you do this kind of demonstration, usually you do that because you're talking about the population. In this case, usually you're talking about your sample. So that's the main difference here. So let's try a few challenges using these variability measures. A typical practice problem for the exam could be standard deviation of my sample is 4. The standard error of the mean is 1. Is my sample size larger than 20? And this, of course, implies that I said that you have to be able to measure these by hand. Of course, it's very useful if you know the formula. And the answer is no, since the sample size is in fact 16, since 4 divided by 4 is 1, because 4 is the square root of 16 and not 20 or anything larger. Is it possible that the standard error of a sample is smaller than its standard deviation? Of course, in most cases it's smaller, and we've seen that in the previous example. That brings up the question, is it possible that these two values are equal? Yes, in a very peculiar occasion, if they're both 0. Other than that, it's always the standard error of the mean, which is smaller. And this last slide shows you a kind of, thinking about how the descriptive measures are characterize each distribution. So these are midterm grades from class A, B, C, and D, from 1 to 5 in each class. First question, what is the population mean in these classes for the midterm grades? For the first one, you would have to find the balance point or simply calculate a population mean, and you would arrive at 3. For the second one, the same frequencies, but still the balance point where you could hold up this distribution and it wouldn't flip to the left or the right will also be 3 and 3, and even here 3, because these are symmetrical distributions, thus the balance point will always be in the middle. But here comes tricky question. Which class shows the smallest variability? This one, this one, this one, or this one? And I'll give you a moment to think about it. And most students pick this B class as their result, but this is not true. It's just that the distribution tells us that every grade has been there with the same ratio, but it doesn't mean that this is has the smallest variability. The smallest variability is where the data points, the individual data points, are closest to the center, which we defined as 3. So it's this distribution with the smallest variability. This is obviously the largest. They're very far from the center. And this is just to give you the actual values in standard deviations. And the bonus problem, a grandmother well-trained in mathematical statistics will prepare plates for Christmas. She has this obsessed idea that she wants the plates to be as alike as possible. Okay, she wants to minimize variability. This is what the plates actually can hold as far as the number of cookies are concerned. So should she choose the square or the round plates? and this is your solution, she should use the square plates because they have less variability. These are the useful formulas for variability measures, and thank you for your attention.